Okay, so in this video we're going to study adiabatic process, but let's start by reviewing the idea of heat and how it depends on the path that you take. So here we have a system, right, that goes from this initial state to this final state. So it goes from this state to this state, and it does that in two ways. It does that by going through this isochoric process and then this isobaric expansion, or this isobaric expansion and then this isochoric process. As you can see, the work done here, for instance, is different than the work done on this path. So you have an internal energy E thermal I here, you have an internal energy E thermal final here. And the change in thermal energy when you go from initial to final here is the same for both processes. So delta E thermal, which is equal to E thermal final minus E thermal initial, is the same for both processes. However, the work done on this process is different from the work. There's more work done on process B than on process A, right? This and both values of works are negative because the gas is expanding, so you're losing energy as you do this. So the thermal energy is a state variable. That is what we mean by the fact that the change in going from here to here is the same for both processes. You can say that by saying that the thermal energy E thermal is a state variable. Delta E thermal is the same for both, and delta E thermal is what? Is the heat on process A, right? The heat on process A plus the work on process A, and that has to be equal to the heat on process B plus the work on process B. These two things are equal. Now this is greater than this. So therefore, and this can only be true, well, this is more negative than this. So this can only be true if the heat through V is greater than the heat through A. So you need more heat to go on to do this process than you need to do this process. So remember the first law of thermodynamics, it says that, well, the change in thermal energy for a system is equal to the work done on the system by the environment plus the heat going in or out the system. So now there are three processes that are important, or that, well, three out of four that are important. The isothermal process, isochoric process is another one, and the adiabatic process. And there is also the isobaric process, but we won't talk about that in this. So an isothermal process is one in which the temperature doesn't change. Because the temperature doesn't change and the thermal energy only depends on the temperature, then this is zero in an isothermal process and the work done is equal to minus the heat. Or all the heat that the system gets is used for work. That's another way to put it. In an isochoric process, the volume is not changing. Because the volume is not changing, there's no work, and all the change in thermal energy, all the heat that you put in goes into thermal energy. Nothing goes to do work. And finally, an adiabatic process is one in which no heat is being transferred. So there's no heat. This is zero. So everything is work in this process, and the change in thermal energy is just work. So for an adiabatic process, one in which Q is zero, right? Remember that that's an adiabatic process. In an adiabatic process, this Q is zero and there's only work being done and the change in thermal energy is just equal to the work. In an adiabatic process, we have this relation that is true. And we'll prove this later in another video. And what that says is that P V to the gamma Gamma is the ratio between the specific heat at constant pressure to the specific heat at constant volume. This is constant. And we are going to use this in many problems because we typically go from a state 1 to a state 2, right? When we solve our problems. And we have P1 and V1 in state 1, and we have P2 and V2 in state 2. So what is true then is that P1 V1 to the gamma has to be equal to P2 V2 to the gamma if this process was adiabatic. So this is true, and we can use this to solve problems. So if we compare adiabatic lines with isothermal lines in a PV diagram, so these red lines are isotherms, the temperature is constant through them. The adiabatics are steeper, right? And so this is an adiabatic expansion, so the temperature goes from this value here to another value here. This is an adiabatic compression. The adiabatics eh, are steeper, and the temperature falls during an adiabatic expansion and the temperature rises during an adiabatic compression. Okay, let's look at this example here. So a gas in a container expands rapidly. When we say expand rapidly, that's a way to say that expands so fast that there's no time for heat to go in and out. So therefore, that's an adiabatic process. So a gas in a container expands rapidly, the same as expands adiabatically, and pushing the piston out, right? So it expands rapidly, pushing the piston out. So the temperature of the gas, as it does that, raises, is unchanged, falls, or stays, or you cannot say anything. Take a minute to answer this question. Well, it falls, right? Because this is an adiabatic process. It's a very rapid process, right? So delta E thermal is equal to W plus Q, but Q is zero, right? Because there's no change in energy. So all this is delta U. So the gas is expanding, it's doing work, so it's losing energy. So the thermal energy decreases, and that means remember that this is equal to NCV delta T. So therefore, this delta T has to be negative, that the temperature falls. So let's look at another example. Here we have an adiabatic compression. Air, air containing gasoline vapor is admitted into a cylinder of an internal combustion engine, right? The pressure is 1 atm and 30 degrees Celsius. So the piston rapidly compresses the gas from 500 centimeter cubes to 50 centimeter cubes, a compression ratio of 10. So what are the final temperatures and pressures of the gas? Show the compression process in a PV diagram. How much work is done to compress the gas? So the assumption we are going to use here is that the compression is rapid with insufficient time for heat to be transferred. So therefore, this is an adiabatic compression. And we'll treat the gas as 100% air. So because it's an adiabatic compression, we know that PV to the gamma is equal to a constant, right? So that means that P initial, B initial to the gamma is equal to P final, B final to the gamma. So I'm going from my initial state to my final state. So from this, I can write this equation here. Remember gamma is Cp over Cv, and I can calculate that for air. And so, these ratios are, well, are given to you, and I'll give this to you if you need it for the exam. So and the ratio is VI to VF is 10, right? That's the ratio. This is the initial pressure. This is gamma. So this is the pressure goes to 25 atms in during this compression. So air is a mixture of N2 and O2. These are diatomic gases, so we use gamma equals to 1.0, which is the gamma for diatomic gases. And so now that we have the pressure, we can find the temperature by using the ideal gas law. And so we can write that PI VI is equal to nRTI, and PF VF is equal to nRTF, or we can write that PF over VF divided by PI over VI. This thing here is equal to TF over TI. And then use this equation right here, and we solve for the values that we know, and we get that that is 488 uh, degrees Celsius. Remember to change this to kelvins here. Uh, so how does this process look in a PV diagram? Well, the gas, this is the isotherm. They need the isotherm for 30 degrees Celsius. This is the isotherm for 488 degrees. So the gas goes, this is a compression, so it's going to go from 500 to 50 centimeter cubes, right? And in that process, it goes from this isotherm to these other isotherms, and the pressure increases by from 1 to 25. So what is the work done? Well, the work done, remember there's no heat here, so we know delta E thermal is equal to Q plus W. There's no heat, so it's just equal to W. So the work is the change in thermal energy. But that change in thermal energy, we know that it's NCV times delta T, where this CV is a specific heat for a diatomic gas. So then we use that equation here. Delta T is 458 kelvins, and the we put the numbers that we know. So we know delta T, we know CV, we know, and the number of moles is found. So we need to find the number of moles, and we can find that from from one of the points. So because we have PI VI is equal to nRTI. So from here we can find the number of moles that is always the same. So you get that is 0.021 mole. And then you put that in here, CV delta T, which you know, and then you get your answer. It's 192 joules. So this temperature that changes dramatically during this compression is all due to work. It's not heat. You didn't heat the system because there was no heat going in or out. It was just work that produced this change in temperature. Let's look at another problem here. We have a gas container that expands rapidly, pushing the piston out. The temperature of the gas falls, and this is because the gas pressure falls, the gas density falls, heat is removed, work is done, both C and D. Take a minute. Well, the temperature falls because work is done. Remember, delta E thermal is equal to, and this is a gas, NCV delta T, which is equal to Q plus W. So now there's no Q here because it expands rapidly. It's a adiabatic process. So the quantity that produced this delta T change is the work. It's the work done here. So it's all due to work.